Hello everyone, my name is Motahare Akhavan. I'm a master student in artificial intelligence from Azhar University. And today I would like to present our recent work, which is titled Graph-Based Feature Selection using Class Feature Association Map or CFAM. Before we get into our proposed method, I'm going to talk about the problem statement and the motivations behind our work. Today, the volume of data is constantly increasing, and one of the main challenges in data mining and machine learning is the high dimensions of the data, which is called the curse of dimensionality. As we know, in the machine learning process, a learning model is created based on training samples, and then this learned model can predict labels for unseen samples. We can think of each data sample as a vector in data space, and each feature represents a dimension in this space. In other words, the number of the features indicates the dimensionality of our dataset. The prediction accuracy of the learning models mainly depends on the feature space. A large number of features leads to reduced model performance, overfitting, and increased training time. So in order to reduce the number of the features, we can use some sort of data pre-processing like dimension reduction. Dimension reduction techniques are divided into two categories: feature extraction and feature selection. In both techniques, the number of features is reduced. However, the main difference between the two is in their reduced feature set. In feature extraction, the feature space is transformed and mapped to a completely new space. In contrast, in feature selection, we select only a subset of the main feature set, and no changes are applied to the initial features. So one of the advantages of feature selection is that since it doesn't change the feature space and keeps features in their original form, it allows more interpretation and readability for future analysis. Feature selection finds a subset of useful features from the initial set based on relevance and redundancy. You can see these two concepts in Figure 1. In the left side of the figure, for separating red class from blue one, we can use F1, so it's a relevant feature. However, F2 isn't relevant because all its values are 0, and it doesn't help in separating two classes. In the right side of the figure, we can use either F1 or F2 to distinguish between two classes of data. In fact, both features have similar values, so they are redundant to each other, and we can remove one of them. Feature selection are divided into three categories based on label information: supervised, semi-supervised, and unsupervised. And from another perspective, feature selection methods are divided into two main categories based on their interaction with the learning model: filter and wrapper. In the filter methods, feature selection is done without interacting with the learning model, and it's only relying on the intrinsic properties of the data. On the other hand, the wrapper methods interacts with the learning model, and in this method, different subsets of features are evaluated by a learning model, and then the subset with the most obtained accuracy is selected as the most important set of features. This method has a really good accuracy compared to the filter method. However, its computational cost is high. For example, for a dataset with D features, we have to check 2 to the power of D subsets of features, which is not practically possible. Our first goal in this study is to reduce the number of features while maintaining or improving classification accuracy. Besides, we want to propose a multivariate filter method. The filter methods are divided into two approaches. Univariate approaches don't consider the relationships among the features, so they can't detect redundant features. However, multivariate filter methods analyze the relevance of the features jointly rather than individually. So they can find redundant and irrelevant features simultaneously. Following that, we use graph data structure to represent the structural characteristics of features using a class feature association map in order to examine the relationships among the features more deeply. Various methods have been proposed for feature selection in different fields, but we will take a brief look at methods based on graph theory. Maybe the most well-known filter method based on graph theory is the Laplacian score, which has been used in various ways in different methods. Laplacian score is based on Laplacian eigenmaps and locality-preserving projection. In this method, a weighted graph with edges connecting nearby data points to each other is created, and the importance of a feature is the degree it preserves the structure of this same graph. Some methods use feature association map concept. For example, in CFAM, a weighted graph is created using Pearson correlation, and then the minimal vertex cover MVC or maximal independence set MIS is used to select a subset of features. The drawback of using FAM is that it ignores the relationship between features and labels and only considers the redundancy among the features. FAST method is another graph-based feature selection using minimum spanning tree or MST for clustering the features and then selects the features of each cluster that best represents that cluster as the final features. CFAM uses symmetrical uncertainty measure to create a class feature association map, or CFAM, and then applies community detection and maximal independence set, or MIS, to extract important features. In some cases, they have used an evolutionary approach to extract features from communities. For example, in MGCACO, ant colony optimization is used for selecting important features. In our proposed method, we have used class feature association map concept to represent the feature space. In our graph representation, each vertex indicates a feature, and each edge indicates the relationships between the two features. In order to construct a weight matrix for our graph, we have introduced a new weight equation based on Spearman correlation. The advantage of using Spearman is that in addition to linear correlation, it also detects nonlinear correlation. According to our weight equation, the redundant features tend to form stronger connections. However, the weight of these connections is reduced depending on the degree of correlation between the features and the class labels. After weight calculation, we use a threshold to generate an adjacency matrix from the weight matrix, so we convert the fully connected graph to a partially connected graph. Then we use community detection to partition the graph. A community is a subset of vertices that are densely connected while loosely connected to other vertices. We have used Leiden community detection, which is an improved version of Low-Vein algorithm. Leiden reduces the possibility of producing badly connected or internally disconnected communities, which can happen as a result of applying low-vein on some graphs. Figure 2 shows an example of applying community detection on the features of masked dataset. As you can see, the graph is divided into 14 different communities, and each community is displayed in one color. To find the most effective features from communities with more than 2 vertices, we use eigenvector centrality. Eigenvector centrality is an extension of degree centrality. However, the main idea in eigenvector centrality is that a node is important if it is linked by other important nodes. A high eigenvector centrality of a node indicates a strong influence of that node over other nodes in a network. So it's a good choice for finding important features. For the rest of the single node communities, we select the vertices with the most variance. Variance score is the simplest unsupervised method for feature selection. The main idea is that the higher the variance of the feature, the more information it provides us. So we tend to remove the features with low variance score. And here is the workflow of our proposed method. As we said before, first we calculate a Spearman correlation among the features and also between features and class labels. Then we construct a fully connected weighted graph based on weight equation. In step 3, we convert the graph to an adjacency matrix using a threshold value, which leads to converting the initial graphs into some subgraphs and some single nodes. Afterward, in step 5, Leiden community detection is applied to the graph for partitioning it into different communities. And in the next step, informative features are selected from each community using eigenvector centrality and variance. And finally, we merge the selected nodes from the 6th step to form the final set of selected features. We compared our proposed method with CFAM method on 5 datasets. You can see the details of each dataset in Table 1. The algorithms are implemented in Python, and for evaluating the selected features, we have used SVM and decision tree learning models. To validate these learning models and also reduce the risk of overfitting, we have used tenfold cross-validation, and finally we have reported 3 metrics. Here are the results of classification accuracy using decision tree and SVM. And as you can see, our proposed method has reached higher or competitive classification accuracy after feature selection. And it also has a better performance compared to the CFAM algorithm. In Table 4, we can see the time needed for training the learning model before and after feature selection. As you can see, the training time has been reduced after applying feature selection. The bar chart on the right shows the number of features before and after feature selection for each dataset. As you can see, our proposed method with green bar has reduced the number of features significantly. In this work, we proposed a graph-based feature selection. Our method reduces the number of features by considering the correlation between features as well as the correlation between features and labels. And it can be used in different applications. We also achieved higher or comparable classification accuracy and also reduced an average feature reduction rate of 70.6% on all datasets. In addition, we managed to reduce the training time to almost half using the selected features. For future work, we can test different similarity or distance measures to provide a better class feature association map for representing the relationships. We can also apply different strategies for finding the most important features from communities. And it would also be valuable to combine feature selection with feature extraction or deep learning methods to reach a more reduced feature set. And here is the references for our presentation. Thanks for your attention.